Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 36, Raster graphics processing, coming from the previous episode where we spoke about WebSocket clients. So for Raster graphics processing, we'll be looking in Python at the Pillow library, which is a fork of the PIL, the Python imaging library. And for Rust, I found the image crate to be very, very useful. And if you want to do some more detailed image processing, like writing true type fonts or do some drawing, then you want to look at the image proc crate that works together hand in hand with this. So those two combined will basically do what Pillow does for you in Python. Let's look at what we will be doing today. So we'll be creating a Julia fractal, which you can see right here. So we will have this output that is fairly big, and then the other example will be producing a thumbnail out of this image. So here you can see the small JPEG image as an output, and up here we have the big fractal that was generated by our image processing code. Let's hop over to the code. On the left, as usual, we have our Python code. So Pillow is a fork of PIL, hence we are importing from PIL to be compatible to the old PIL code that you might already have. And there we use the image. And to do our fractal code, we will have to use NumPy. And that's already what we start with. We have our Julia function, as we do on the right in Rust. In Rust, we would import from the image crate the filter type and image formats that we need to provide as enums to certain functions. And the path buff will be used to create a buffer from the command line argument parsing. Right, so Julia function on the left and on the right will produce an image with 800 pixels in a dimension. And then I've copied an example code to have the Julia fractal be computed from Rust. So here we have to, as always, make sure that is the correct data type. So here we start with an integer, but we have to process as a float. In Python, we don't have to do that since this side already is a float. The whole computation becomes a float. We don't have to do any type mangling. Then we create an image buffer. So for Python, I decided to use the numpy zeros array that then gets set up with the width and height of the image plus 3 bytes per pixel, which then would hold the color information red, green, and blue. So here we have a minimal data type of doing RGB image processing in a raw data form. On the Rust side, we simply create an image buffer that already knows how to treat those 3 color information pixels, so we just have to provide width and height to that. Let's look at the loops. So on the left, on the Python side, we would loop over the NumPy array. Since we are giving a shape of 3 elements, the index will be the coordinates x and y actually in a tuple. The x and y coordinates will be used to create this gradient background color. So that's why we are here using x and y for red and blue. And later down here, we do the calculations to come up with our green color, the Julia fractal that we can see. We start off with the green color being 0, so no green applied whatsoever for this pixel. And then this loop here decides how intense the green will be. As you can see here, it gets incremented by 1 every time this condition holds true. At the very end, we take our image buffer's index and write the red, green, and blue variables to the pixels. And here we can then use the images from array static method to create an RGB image from the image buffer. Once we have an instance of our image object, we can then save it to a PNG file. On the right, this is very similar. Here we get to use an instance method called enumerate pixels mute. So this gives us the coordinates of the pixel and the pixel itself. with a mutable reference to it. What we can do now is the same math as on the left, but since this is Rust, we have to make sure that we are typecasting the coordinates of the pixels, which are integers, to floats. Here we can see the difference that complex numbers are part of the Python library, and on the Rust side we have to use a crate for it. Further down we get the loop again for our green color, and then we dereference the pixel and set it to an image RGB value. And here we hand off our slice with the values red, green, and blue. After we have done that, we can use our image buffer instance to save out to a fractal PNG. Since this can fail, I decided here to not do proper error handling, but just unwrap the error. The program will fail if there is a problem. The program will halt if there is a problem. At the bottom, you can see that the main code is already starting. Let's look at that. Here we can see on the left that we run the Julia function that I just described. And below we go over the command line arguments that have been passed to our application. So in Rust, this is fairly easily done. You use the sys arguments and you loop over everything but the program itself by using this slice denotation. Once we have done that, here we can use the split extension code to split it into file name and extension. Only use the left part of this and attach our new extension to the file name. To be sure we are not overwriting anything, even though we just mangled this file name into a new form. We do double check if it is the same. If it's not, we actually write out the thumbnail. To resize is very easy with the Pillow library. All you have to do is you open the file. And once you have the image, you call the thumbnail function with the dimensions that you want. Once you have done that, you can save it out into the format that you desire. And the problems we will simply catch with an exception handler. On the Rust side, we also call Julia function. And then for the command line arguments that have been passed to the application, if you don't want to use a fancy library and just directly treat it as we did here in Python with the sysargv, we can use standard environments args iterator. We skip the first one because we don't care about our own application's name. We want to have the arguments passed to it. That will be then the file name. We then create our path buffer to have a source file name, and from the same file name we create a thumbnail path buffer. The cool part in Rust is we have now a library method that lets us set the extension of the file, so we don't have to do any complicated tricks. We simply replace the extension with what we want. Then we also make sure that those two names do not match before we write the thumbnail. After that, we open up the source image from the source path with the image open function. And from there, we then use the reference of our source image for the image ops resize function. Here we also provide our dimensions, and we get to choose which filter we want to use. I found that this Ketmal ROM gives a good result, but you might choose one of the other options. Once we have done that, we can use our source image and save it out to another format, now with the new path name that we've created up here. Here we have the image format enum. So these were the imports that we used before, the filter type and the image format. And since this saving can fail, we use unwrap, which is the easy way out into exception handling, which is done here more nicely on the Python side. So that concludes this code. I hope this small example gave you a good idea of how to create your own raster graphics or do some simple processing on existing raster graphics. Thanks for watching. Coming up next on the From Python to Rust series will be vector graphics processing.